Alright, 3.3, solving systems of inequalities by graphing. Buckingham students will be able to solve a system of inequalities by graphing and determine the vertices of a region formed by the graph of a system of inequalities. Alright, basically what that means is we're going to solve systems of inequalities. So in a system of inequalities, the solution for that is going to be an infinite amount of numbers. So the only way to solve it is to make a graph. So let me show you what I mean. Let's do this guy first. This little y is absolute value is less than or equal to 3 is a little tricky. We got to go back to what we first learned about solving for absolutes, and we have to split it to y is less than or equal to 3 and y is greater than or equal to negative 3. So when we graph this, it's just going to be two straight lines, one right here at y equals 3 and one at y equals negative 3. Okay, and look, y is less than positive 3 and greater than negative 3. So that means that we're going to be shading somewhere in between. But I'm going to wait to do all that shading for just a second because I still want to graph this line. And this line looks just like y equals x plus 1, but it's going to be dotted. I'll do this one in blue. So plus 1, I go right here. Looks like my slope is just 1. And should have done it dotted, so let's just go like this. Alright. Now I have my dotted line, and it says y is greater than, so that means I'm going to shade on this side. And now I can shade all inside all these boundaries that they gave me. And all of those points going on and on forever to the left are solutions to these inequalities. So that's why we have to do a graph, because we can't write down the solution because there's an infinite amount of them. But we can at least graph it and get an idea or a region where we know that there are solutions. Okay, I want you guys to try practice number 1 on your own, and I'll put the answer up there in just a second. Okay, here's what your two lines should look like. Here's the top line, it's dotted. Here's the second line. And it says that we're going to shade greater than the red line. So we're going to shade up on the red line, but less than on the blue line. So below the blue line. So that's this area. Greater than the red, but less than blue. And so all of that is our solutions for these systems. Okay, let's go on to this next one. This is an interesting situation. I want you guys to graph it, because you guys should be able to graph these. And then we'll talk about it in just a second. So go ahead and graph it. I'll put the graphs up there as well. You can check and see that you graphed it correctly, and then we'll chat about it real quick. Okay, hopefully if you graphed it, you got two parallel lines, you dotted them. On the top line you shaded up, on the bottom line you shaded below. Now, what's interesting here is we don't have ever a time where there would be overlap. Notice in all these other ones, there was overlap. Okay, there was overlap here, there was overlap here. This is where we would have shaded for both. I only shaded for one on both, or for the overlap here, but if you were just shading for red, you would have shaded all here, and if you're just shading for the blue, you would have shaded all here. So here I'm showing you that there's no overlap. So whenever you have an inequality, a system of inequalities where there's no overlap, that means that there is no solution. It says that. In fact, it says that down here. If there are no shaded regions that overlap, then there are no solutions to both inequalities. That's what we're looking for, solutions to both inequalities. We have either or, but we don't have any that are for both. Alright, let's go to the next page. In 1959, NASA wanted astronauts who were at least 5 feet 4 inches, but no more than 5 feet 11 inches tall, because of limited space inside the Mercury capsule. They were to be between 21 and 40 years of age. Write and graph a system of inequalities that represents the range of heights and ages for qualifying astronauts. It's funny, I just was watching a movie on this very topic, a movie called The Right Stuff, where they were looking for the first astronauts. So 5 feet 4 inches, 5 feet 11 inches, that's kind of hard to write on a graph. But what we could do is we could convert that to inches. So 5 times 12 is 60, so this is like 64 inches. And 5 feet 11, that's like 60 plus 11, which is 71 inches. And since we're only dealing with 64 to 71, I'm going to make the bottom my inches. I'm going to make this my age. And I'm going to do the little thing where I told you guys before, if you're graphing, you can just draw one of these guys, just a like quick squiggly line. And that just means we're going to skip a whole bunch. And let's just make this 64. Let's see, can I fit it all the way to 71, 65, 66, 67, 68, 69, 71? Yeah, so let's just do that. Now we can fit a nice big graph there. I didn't have to do that, by the way. I could have made these like go by tens, and then I would have just graphed a really narrow region, and that would have been just fine too. A couple different ways we could do this. Alright, for age, let's zoom into age. I'm going to make these like every 5. So this is going to be like, that means every 2 is going to be 10, so 10, 20, 30, and there we go, 40. Alright, well, let's write our inequalities here. For age, well, they said it has to be less than or equal to 40, because it has to be between 21 and 40, and I think that could be equal to, right? Because if somebody is 21, once they turn 21, that means they are at least 21 years old. So, and we'll say that means they're between 21 and 40. And then for height, we said, right, less than 71, less than or equal to 71, but greater than or equal to, 64. So let's graph this. Remember, age is going up and down, so my upper boundary for age is 40. My lower boundary is just over 20. My lower boundary for height is 64. And my upper boundary for height is 71. And now I just shade in here. And there we go. That's my feasible region, or my possible region for astronauts. Of course, there's a lot more requirements than just that, but they had to be within this region to even be considered. So, pretty neat. Alright, let's go to the next question. Okay, we're going to just graph a bunch of these lines. I notice that they're all or equal to, so they're all going to be solid lines. I'm going to color code them. Let's do the top one. X plus y is greater than or equal to -1. So I'm going to cover up my y, and I get a y-intercept of -1. I cover up my x. I'm sorry. When I cover up my y, I get an x-intercept of -1. So this line's looking something like that. Remember, this one's actually asking us to find the vertices or the corners, so that's going to be our last step. We have to do that eventually. Alright, let's graph the red line. If I cover up the x, I get a y-intercept of -6, so let's do that. And if I cover up the y, I get an x-intercept of +6. Okay, right away I already see that corner is going to be a little bit tricky to find. Okay, and let's graph the blue one. Now the blue one's going to be kind of weird. If I cover up the y, I get an x-intercept of 32. Okay, I don't have 32 in my graph, but I'm going to just go way out here and I'm just going to say, hey, there's a point out here, 32, 0, and I know that. Okay, if I cover up the x, I'm going to get, let's see, let's just solve it out because it's kind of tricky. I'm going to get 12y equals 32, divide by 12, divide by 12, and I get y equals 32 over 12. I could reduce that by 4, giving me 8 over 3. Okay, well that's not going to be really easy to plot. 8 thirds, it's 2 2/3. So I know that it's somewhere around here, but that's not really accurate for my graph. I want to get some things that are right on the coordinates, because the whole point of this is for me to find the vertices. So here's what I'm going to do. Remember I said that this is out here at 32, 0. Okay, well, if I could somehow figure out the slope, I might be able to work backwards and find some other points on this line. So let's go back and look at the slope then. Alright, so the slope is negative a, which is 1 over 12. Ah, okay, now I got something. And that's the same thing as positive 1 over negative 12. Now, let's think about that. That's my slope. It's 1/12, or negative 1/12. So that means if I was going backwards, I would go up 1 and then back 12. Well, what would that look like, up 1 and back 12? Well, it would be up 1 would be here. That'd give me a point of 1 for my y. And if I went back 12 on my x, that'd give me a point of 20. Well, I'm still not on my graph, but I'm getting closer. Let's see, maybe I could go up 1 again to 0.2 and 0.8. And 8.2 is on my graph, so let's plot that. 8.2, there it is. And let's go one more time just to get a good perfect line. If I go back 12 and up 1, well, look at that. I got another point on my line. And it happens to go right through my y-intercept. And now I'm graphing it like perfectly. Okay. If I was to shade all these in, let's look at how we're going to shade this. None of them are solved for y, so I think the easiest way to shade is to plug in 0, 0. So I got a 0 and a 0, that would just be 0, which they say is greater than negative 1, which is true. So for the black line, I'm going to shade on the 0, 0 side. Okay, so I know I'm shading up here. And for these, I recommend maybe just drawing a little squiggly on one side so you know which way you're shading on. Alright, for the red line, 0 minus 0 is 0. Is that less than 6? Yes, it is. So I'm shading on the 0, 0 side for the red line. That's that side. And for the blue line, if I plug in a 0 plus 12 times 0 is still 0. Is that less than or equal to 32? Yeah, it is. So I'm shading on this side for the blue line. That overlap region is all here. Okay, so now I've graphed these things. And these points are pretty easy to find. We could see this one is at negative 4, positive 3. So there's one corner. And this one we already said is at 8, 2. But how are we going to find this one? That's going to be a little bit tricky. Now, I could kind of estimate it just by looking at the graph, but that's not going to give me an exact answer. So I'm going to have to actually go back to algebra and solve this one. I know it's the black line and the red line, which is these two. So I'm going to go over here and use a little algebra and solve for these real quick. So x plus y, I'm going to just pretend like it says equal to negative 1, just to solve for where they intersect. And x minus y equals 6. Well, I can use elimination and just add these together and I get 2x. My y's will cancel out, equals 5. So x would equal 5 divided by 2, or 2.5. Okay, so now I'm going to plug that back in. Let's do x plus y equals negative 1. Plug that in for x. So I have 2.5 plus y equals negative 1. And I'm going to subtract 2.5 from both sides. And I get y equals negative 3.5. Okay, now let's go to our graph and let's see if these points make sense. Does x look like it's at about positive 2.5? Yeah, it does. And does y look like it's at negative 3.5? 1, 2, 3.5? Yeah, it does. So that's our missing coordinate here. It's 2.5 comma negative 3.5. Alright, I know that's a long problem. You're going to have some like that, so they take a little bit of time. Last thing I want you guys to do is write a system of inequalities where the solution set would be a square. Or if you're up for a challenge, how about an equilateral triangle? So think about that, give it a try. I'll see you guys on the next video.